All right. Let's see. We have a question from Rohan Katakodi. Rohan, are you able to unmute and turn on your camera?
Hello. Yeah, just a second.
Hi, Rohan.
Am I visible? And is my camera? Am
You're
I
not,
visible?
you're audible. And I think that's the important part.
Okay. Right. So great talk. And I have a question. You mentioned that iGUARD is around 15 times faster than Barracuda. And my question is,
Oh dear. Well, that's a cliffhanger, because I think he cut off right after the word question. So Rohan,
yeah,
take a second attempt.
yeah, hi. Can you hear me now?
Yes.
Yeah.
Okay, great. So, my question is that is all the performance difference coming from the in-GPU detection of iGUARD, and is Barracuda fundamentally incapable of performing in-GPU detection, or can it be modified to do so?
That's a great question. So yes, we believe a lot of the performance is coming from the in-GPU detection. So how Barracuda basically works is they instrument the PTX, which is an intermediate representation of the GPU code. They instrument that, and on memory accesses and on synchronization accesses, they note down like the address being accessed in a buffer that they store on the GPU. They have CPU threads, which are constantly reading from the GPU buffers, and then the CPU threads perform the actual race detection. So the advantage of that is CPU threads have a bit more flexibility. Like one problem we found in GPU is that dynamic memory allocation is bad for performance. Another is like pointer chasing on GPUs is does not perform well. So the advantage of shipping stuff to the CPU is you could do like pointer chasing, you could do dynamic memory allocation. You could keep track of all of these elements on the CPU side much easier than you can on the GPU side. But as we mentioned in our paper, this adds performance overheads because you have hundreds of thousands of GPU threads generating data. This data is being shipped to the CPU, and you have not as many CPU threads performing the race detection. So there is some serialization that gets involved in this process. I hope this answers your question.
Yeah, yeah, thank you.
Yeah.
Wonderful. So we have a question in Slack from Yunfeng Chen, who I believe is here. So Yunfeng.
Hey, great work. Can you hear me?
Thank you. Yeah, we hear you.
Yeah, I think iGUARD uses a kind of migration technique to provide the actual virtual memories. So I think will this migration of the metadata spoil a lot of performance when it frequently access to the different portions of the metadata? I mean, have you an evaluation for this?
Amazing question. I love this question. The answer is, so what we do, I'll just explain the metadata migration to everyone first. So we make use of a feature called as UVM, which is Unified Virtual Memory, which basically allows us to allocate more memory than the GPU memory has. And on a page fault, that's when the actual memory, physical memory gets allocated. And if we end up using more memory than the GPU has, then some of the data gets stored on the CPU memory. And then when we start accessing data, the data gets migrated between the CPU and the GPU. And why we do this is this allows us to exceed the GPU's limited memory. So for example, I think the modern A100, the maximum GPU memory size is around 80 GB, which is a server class GPU, but most servers have like TBs of memory. So this allows us to make use of the CPU's excess memory for race detection. So your question is basically, would this migration hurt performance? So what we do is we instrument every memory allocation and deallocation that occurs, which is like CUDA malloc and CUDA free. And we keep track of how much memory the application is using. And we calculate how much metadata we would need. And if we find that this does not exceed the GPU memory, then we proceed to allocate everything on the GPU memory itself, and we don't perform the whole migration technique.
Yes.
However, if it does exceed the memory capacity, then yes, some memory will be allocated on the CPU and migration will take place. In our paper, we have a small experiment where we scaled the memory sizes, and we showed like performance remains relatively stable until the GPU memory size is exceeded, in which case you will see a small spike. But prior work like Barracuda, they fix a certain amount of GPU memory for race detection. And because of that, when this memory constraint is exceeded, their detector basically fails. It's not able to perform detection. We are able to perform detection, but yes, you will see a performance penalty when the limited capacity of the GPU memory is exceeded. Thanks for the question.
Yeah, thanks.
All right. We have a question from Shudong Sun.
Yeah. So I noticed that in the presentation video, you mentioned that when iGUARD detects a race, you will provide the instruction pointer, memory address, and the race type. So I was just wondering, like, can you provide any suggestions that how one can use those information to localize the bug in the source code and to like further fix it?
So if you compile with the flag called -line_info, then iGUARD will provide you the exact source code line and the file in which the code is. If it's not compiled with that, then that means your binary does not contain that information, which is why we provide the instruction pointer instead. But if you have the source code, it's better to compile it with -line_info, and then we'll get you the file name and the line number where your data race exists.
That's great. Thank you.
Yeah, thanks for the question.
All right. Well, I'm going to exercise session chair privilege here and inject one of my own questions. And what I'd like you to do, Aditya, if you would, is reflect a little bit on the distribution of bugs you actually found. And to frame that reflection, I'd like to note for the audience members who aren't aware, some of the software code bases you evaluate against significantly predate the synchronization primitives that you're looking at, right? So Lone Star was developed in 2012 and ITS didn't come out until much later, right? So what, when you found all these bugs, is it because those codes were mostly written under assumptions that violate the ITS, conditions of relaxing the sort of barrier synchronization between instructions, or is it actually abuse of new primitives mostly? Does it make sense?
Yeah, that makes sense. So we did find some new bugs in ITS. For example, we found a code where they assumed every warp is synchronized after every memory instruction. So they did like some if conditions. If the thread ID is less than this, do this. And they assumed that between every if condition, there would be a synchronization because it was within a warp. So that did get detected as breaking ITS. There were also just some regular bugs that we caught, which were not related to the newer synchronization. But it's a mix of both, basically.
Okay. And I'm going to indulge myself with one more question. You talk a little bit about inferring locking protocols, and I think the many people who've studied synchronization will have some sense of how you can look at a sequence of instructions and determine whether it's implementing a lock. But you have to take this one step further and infer the scope. I'm wondering if you can try to provide a little bit of intuition about how you can do that.
Okay. So yes, we do inferring locking protocols. So what we do is we have a lock table. So on an atomic cast, which is typically used for a lock acquire, we insert an entry into the lock table, and we have a bunch of bits in the lock table, which is like valid, active, and scope. So we insert it into the table and we set the valid bit. But to fully complete the lock acquire, you also have to have a fence, a thread fence. So on a thread fence, we set the active bit of that previously atomic inserted into the lock table. And then based on the scope of both of these operations, we set the scope bit. So if both of them are device scope, then it is a device scope lock. If either of them are block scope or both of them are block scope, then it's a block scope acquire, because the smallest scope ends up taking precedence. And same thing for release, we remove it from on a thread fence. Yeah, and on an atomic exchange, we remove it from the lock table. So there is some semblance of scopes, and that is also stored in the metadata.
Okay, thank you for that answer. And I think at this point, it's a reasonable point to transition to the second paper. So
all right. So now is Q&A. So I'll ask for the person who asked a question. So please first briefly introduce yourself. Let's see. Well, we don't see any questions yet. So I'll start by a question. So I'm Ding from University of Toronto. So it's interesting work. Can you comment a little bit about like the bugs you found? Like what are the consequences? Like because I'm not familiar with these GPU applications. Like will they lead to crashes or wrong result or what?
Okay. So a few of the bugs we noticed like deadlocks would occur because of improper synchronization. But what I'd say is more deadly are the races which didn't actually create any noticeable bugs. Because say you have an incorrect output, right? Then it's easy to go back and like put output statements or use GDB and try to find where you're getting this incorrect output. That's easy to do and pinpoint and then figure out like, oh, okay, I have a race. What's worse is if it doesn't cause any issues, and then suddenly, like say one compiler generation later, or you buy a new GPU and you run your program and suddenly nothing works. Like it was working for like so many years and then suddenly with the next GPU generation, it breaks. And I feel that's a bit more deadly and that's more where iGUARD's usefulness might be a bit more because these races might not manifest every time you run it or on every GPU generation or every compiler generation, but there's still bugs.
I see. That is interesting. Then a follow-up question is that, do you mean that some of these bugs are so-called, like legacy bugs where they don't manifest in some older GPUs, but they will manifest in newer models, just like, we see suddenly a lot of kernel concurrency bugs after we have multi-force?
So like there are related papers. There was one in ASPLUS, I think, where they tested out a bunch of concurrency bugs on multiple GPUs, like missing a thread fence, missing like general concurrency bugs. And they found like different GPU generations behave differently. In some, there are absolutely no incorrect outputs. It behaved perfectly. In some of the older versions, there were some bugs. So yeah, it could be GPU dependent.
I see.
That is a possibility.
Yeah, okay. All right. So let's see. Audience questions. Oh, there we go. How do I promote? Do I have to promote the audience to the panel or the? I'm sorry about this. Yeah.
So hello, can you hear me?
Yeah.
Hello.
Here is Shixing Zhao from the University of Hong Kong. So thanks for a great talk. I have a short question. So is it possible to apply the approach like static analysis to the GPU bugs before runtime? Or it's not possible because too many false positives? So another short question is, do you have any suggestions on how to fix or avoid such bugs? Thank you.
If I understand the first half is, can you use static detection beforehand before performing the dynamic detection? Is that right?
Yeah.
So we have not done that, but that could be done. And so I'll give you one example possibility. In many GPU kernels, we noticed some data is used as purely as input data and was only read from. So you could perform static detection beforehand, try to identify those data regions which are only read from. And then you wouldn't need to perform dynamic detection on those data regions because you already know they're not going to be written to. So you could like reduce performance overheads by performing a passive static detection beforehand. Yes, we have not done that, but that could be an interesting like future work. I couldn't catch the second question you had.
Do you have any suggestions on how to fix or avoid such bugs?
How to avoid such bugs?
Yeah.
Go through the documentation very, very carefully. It's a bit confusing. So it becomes like a performance versus correctness trade-off. Like, for example, we have scopes, which they provide thread lock and device scope. If you use the largest scope, you reduce the risk of any incorrect behavior, because the larger the scope, the more threads it synchronizes with. But if you use a smaller scope, you have to be careful that you're actually only synchronizing within that scope of threads.
So do you mean if you are using such a advanced features in new GPUs, so you have to face such obstacles to have some?
Yes. Yes.
Thank you.
If you're using advanced features, you should be very careful that you're actually using them correctly.
Okay.
But again, it's a performance trade-off. You could potentially get better performance by using them.
Thank you.
Thanks for the questions.
Okay, so let's take the next question. In Hong, are you the one asking the question? Okay.
Hello.
Yep.
I'm Tim from Hong Kong also. And I see that you are a runtime tool, so I wonder what is the performance overhead here? So will it increase a large performance overhead in terms of like computation time and storage? Yeah.
Where are the performance overheads coming from? Is that your question?
Yeah. So iGUARD is a runtime tools, right?
Yes.
So you do the detection at runtimes, right?
Yes, exactly.
So what is the performance overhead here? So since you are doing the detection at runtime, so
are you asking how much or where is it coming from?
How much? Yeah.
Okay. So on average, we found the runtime overhead to be around 5x, which means if the application took like, say, 1 minute to run, with iGUARD, it would take 5 minutes. Or yeah, 5 minutes.
Okay. So do you suggest that you will run the tools like while you are running the applications, or you would use it as a fuzzing tools or something like that?
So I would recommend using it as like a debugging tool. So you'd like write your program, you'd run it using iGUARD once, check if there are any races or anything, go back, fix the program. So while you're iterating on your, while you're writing your code, you keep using it as a debug tool. And then once you're done, you just run it without iGUARD. So it would be like something like Valgrind, stuff like that. You just use it when you're debugging. You wouldn't use it in your final production.
Okay, so will we miss some bugs that is really existing in the real running? Is it possible?
Can you repeat that?
So while you're using the tools for debugging, you find some bugs and you fix that, and then you are using like some real data, and it will like you have some race, but you did not detect it while you're using the debugging data. Is it possible in your tool?
I believe it is, yes, because it happens before, has the problem where if a race does not manifest during the detection process, it will not be caught. So there could be like certain interleavings that certain like threads being scheduled that did not actually end up happening during your detection pass, which ends up happening during your final run, and that might cause a race to not be detected by iGUARD. Yes, that is a problem with dynamic race detectors in general.
Okay. So do you test the like how many of them will exist like in your data sets or workloads?
So from the workloads we had, there were some workloads which we already knew had races. And for those workloads, we were able to catch all of them. We didn't have any cases where like some did not manifest. There were some cases where like we had to run it multiple times before everything was caught, where like the first pass might not have caught all of them. But I think within like at least 3 runs, all the races were caught.
Okay, that makes sense.
Okay. Thanks for the question. Yeah,
that's a lot.
Right, and we have time for another short question.
Hi, this is Lishan Yang from the College of William Mary. I do have a short question. Have you considered the overhead of scalability issue? Like if you apply your iGUARD to GPU clusters, either large scale GPUs or heterogeneous GPU clusters?
So you're saying like multi-GPU clusters, right?
Yes.
We have not done that thus far, but this was also brought up in the morning session. And I think it's a very interesting problem to look at, looking at races across multiple GPUs or with the GPU and CPU when they access common data. We haven't done that, but we believe our framework could be extended to support that. You could instrument like, so there's like CUDA malloc managed, which allows you to access data from across the CPU and GPUs. You could instrument that instruction, keep track of which data is being shared among multiple GPUs, and try to perform race detection on that. That would be an interesting thing to look at. Yes, but we have not done that.
Yeah, thank you very much.
Yeah.
All right, great, thank you. So let's move on. Our next presenter is Sishuai Gong, who is a 3rd-year PhD student at Purdue University.